Hello and welcome to lab number 7, titled Laser Beam Steering with Right Angle Prism. In this lab we are going to learn about another important optical component that's called PRISM. We're dealing with a three-dimensional optical component with a triangular base that's very often used in different types of optical devices. Specifically, it's used for pattern recognition, for beam steering, interferometry, etc. So we are going to perform a few experiments here with right angle prism, and we are going to observe two important phenomena related to the light. First being light reflection and second being light refraction. There's a few learning outcomes for this lab. First, we are going to learn how to trace the light rays that are traveling through a prism. And then we are also going to verify the law of refraction and the law of reflection. We are going to demonstrate the total internal reflection in a right angle prism, and finally learn more about this important optical component that's being used in photonics. The equipment to be used in this lab consists of a laser pointer. I'm going to be using here an affordable laser diode, red laser diode. You can use any other type of a class 1 laser point, either red or green. And then we are also going to use a right angle prism. For our measurements, we are going to use a protractor. We are also going to need the pencil and finally a big white sheet of paper. To accomplish learning outcomes for this lab, you need to complete the following steps. Number 1, you're going to tape the white paper to the top of your lab desk, and you're going to place the laser pointer on one side and you're going to tape it down so that it's held steady. The next step is to place the right angle prism on the path of the laser beam, but before we do that, I would like to point out that it's very important to keep this right angle prism, this optical component, free of any dirt or fingerprints. If there's any dirt or fingerprints, you have to implement proper cleaning procedures that are going to be covered in a different lab. And if your right angle prism is clean, you would want to make sure that you're holding it for its edges so that you don't introduce any kind of fingerprints that may skew your results. After we positioned our laser pointer and taped it down onto the white sheet of paper, we also placed our right angle prism, as shown here, approximately at an angle of 45 degrees relative to the constructed line in the previous step. And then we turned on our laser pointer, and what we can observe here are three distinct laser rays. There's an incident ray that you can see here that's getting out of the laser and hitting the prism. And then there's two distinct phenomena that you can also observe here. One being a reflection, so you can see a reflection of the laser beam here on this side off of the prism, and then also over on the other side you can see another beam, the beam that passed through the right angle prism, and you can also see that the path of this beam have been skewed in a specific direction due to so-called light refraction or bending of the light. So the purpose of the rest of this lab is to trace these rays and then apply the Snell's law of refraction and law of reflection to figure out at what angles these laser beams are leaving the prism. In order to do that, we are going to hold the prism steady, and we are going to establish or draw an outline of the prism on the white paper, and then we are going to trace these laser beams by using and marking the dot, using our pencil and marking the dots along the beam. So every time the laser beam hits our pencil, I'm gonna try to tilt it here a little bit for you to see. You can see here how the laser beam is hitting the pencil, so that's going to be one of our dots, and then there's going to be another dot right here, and then a few more dots on this incident light ray. And then over on the other side, we are also going to mark a few dots along the reflected ray. And then also a few dots here along the refracted light ray. Now that we marked three light rays, we are going to remove the prism And we are also going to turn off our laser pointer. And then we are going to construct the lines by connecting our dots. So this is our incident light ray. And here's our reflected light ray. And finally, over on the other side, we have a refracted or bent light ray that passed through the prism. We are also going to improve our footprint of a prism. So once more, this line here represents incident ray. Over on this side we have reflected light ray, and finally, as a third light ray over on the other side of the prism is going to be our refracted light ray. To provide more space, I have removed the laser pointer out of the way, as well as the prism. And now we have our diagram, so we can see the footprint of our right angle prism, and we see three light rays here: incident light ray, reflected ray, and refracted ray. So let's start with the reflection. So if you are looking at this point here, that's where your incident light ray hit the prism, and then it got reflected in this direction over there. So the first step to confirm the law of refraction is to construct the line or the axis that's perpendicular to the surface where the whole reflection took place. So this face of the prism right there is where reflection took place. So we are going to label this point here as a point A. So this is our point A. And at that point A, we are going to construct the axis that is going to be perpendicular to the surface, to this surface of the right angle prism. So the way we are going to do that, we are going to use the protractor. The protractor has this line here that we are going to align with the side of our prism. And then over here, we're gonna label 90 degrees and then connect these 2 points. And I'm gonna use the dotted line here to indicate the axis that's perpendicular to the surface of the right angle prism. And I'm also going to extend it over to the other side. Now we can observe 2 angles here. The first angle is going to be the angle that incident ray makes with the axis. So that is going to be this angle here. We are going to label this angle as theta incident. And then another angle that reflected light ray makes with the axis is going to be this angle. That is going to be labeled theta reflected. According to the law of reflection, these 2 angles have to be the same, and that's what we need to confirm in this experiment. So in order to confirm that, we are going to use the protractor again. So we are going to position the center of the protractor here, align it with this incident light ray, and then we are going to measure the angle to the axis. So you can do it this way, or if you wish, you can look at the axis as a 0-degree line. So you would want to put your protractor in this direction. So right now your protractor is aligned with your axis. It's aligned with the axis. And we're measuring the angles. So we're gonna go here like that. 0 degrees, 10, 20, 30, 40. It's about 46 degrees, right? So if you measure here, it's about 46 degrees. So there's a 10, and we have 20, we have 30, 40, 45, 46. So our incident angle, theta incident, is about 46 degrees. Obviously, your measurements may be slightly different than mine based on how you aligned this prism here relative to the beam of your laser pointer. And then we're going to measure the angle over on the other side, or reflected angle. So again, we're going to put the protractor here. So we're going to align with the axis, and then we're going to use this scale, right? So if you look at this scale here, there is a 0, and then we have 10 degrees, and then we have 20, 30, 40, and then we have 41, 2, 3, 4, 5, 46 degrees. So we are measuring theta reflected being equal to 46 degrees. So if you compare the theta incident being 46 degrees to the theta reflected being 46 degrees, we have confirmed that law of reflection holds, meaning theta incident or incident angle is equal to the theta reflected or reflected angle. As a next step, we are going to do the measurements related to the bending or the refraction of the light. This part of the lab very often is overlooked and confused, and it's very important to be understood in the proper way. So it's very important to observe that two refraction-related phenomena are taking place here. The first refraction is happening at this surface here when the light is passing from the air into the medium out of which the right angle prism is made, and then at this point here that I'm going to label as a point B, so this is my point B, that's where we have a second refraction where the light is leaving the medium of the prism as entering back into the air. So it's very important not to be confused and perform the measurements on the original incident beam and the secondary refracted ray. You would want to either perform the measurements at point A or at the point B. So we are going to pick the point A, and for the point A, we also want to create another refracted, or you may call it a primary refracted ray, and that is going to be the ray that's passing through the medium of the prism. So by connecting the points A and B, we are going to create that refracted laser beam. So I'm going to make it a little thicker here to kind of emphasize this direction. So again, the incident light ray is hitting the prism at the point A, and then it's being bent or refracted along this line here to the prism. That would be our primary refracted ray. And again, here at the point B, we have a second refraction, second bending, where this final refracted light ray is being created. So what we want to measure the incident angle, which is our previous theta incident, and then we also want to see the angle of the primary refracted light ray, which is this short stretch here, relative to the axis of the axis that's perpendicular to the surface of the prism. So in order to do that, I'm going to extend this primary refracted light ray a little bit. So I'm going to do it this way. So once more, I'm also going to label this short stretch here. I'm going to call A, B. I'm going to call this primary refracted ray, and I'm gonna add word secondary in front of my previous label. Now my refracted angle is gonna be the angle that a primary refracted light ray makes with the axis perpendicular to the surface of the prism, which is going to be this angle here. So this angle here is going to be labeled as theta refracted. Let's now measure our refracted angle. So again, we are going to use the protractor, position it along the axis, and let's see how much we are going to measure now. So from here we're measuring 10 degrees, 20, almost 30, so about, let's say, 29 degrees. So we're measuring 29 degrees for the refracted angle. So we are going to record it here as theta refracted equal to 29 degrees. And let's now use Snell's law of refraction to come up with the value for the index of refraction of the medium of the material that our right angle prism is being made of. So our incident angle is equal to 46 degrees as measured before. Our refracted angle has been measured as 29 degrees. And then here's the Snell's law of refraction. N1 times sine of theta incident is equal to N2 times sine of theta refracted. Now we are going to substitute for N1, index of refraction of the first medium, which in our case is air, is equal to 1 times sine of 46 degrees, which is our incident angle, is equal to N2, which is going to be our unknown index of refraction of the material that the right angle prism is made out of, times sine of the refracted angle, which in our case is 29 degrees. Now we are going to perform the calculations. So first we're going to do the sine of 46 degrees. Comes out to be 0.719. 1 times 0.719 equal to N2. Let's do sine of 29 degrees. Comes about to be 0.48 times 0.48. We can round it to 0.485. And then from here we can calculate N2 as 0.719 over 0.485. if we do this calculation, 0.719 over 0.485, we get the value of about 1.48, which is very close to 1.5, which is what we would expect to see, because this is some sort of glass-based material that this right angle prism is made out of, and we know that index of refraction of the glass is about 1.5. So we are pretty close, 1.48, if we take into account that we did a few of roundings here, and we take into account certain measurement errors, we can easily justify the value that we came up with. That's actually very important. You always want to make a sense out of the measurements that you are doing. Even if you are off of the expected value, you would want to be able to explain why you are seeing certain inaccuracies and how to make sense out of specific type of a measurement that you performed. In this second part of the lab, we have slightly adjusted the position of our right angle prism. As you can see right now, our laser beam is hitting the right angle prism at the right angle. In other words, the angle between the axis and the incident beam is equal to 0 degrees. It turns out that in such a case, it can be very easily can be confirmed using a Snell's law of refraction that the light that is refracted into the prism is also gonna continue along the same path. In other words, it's not going to be bent. So that's an important rule that can be proven using a Snell's law of refraction. In other words, when incident angle is equal to 0 degrees, then the refracted angle is also going to be equal to 0 degrees. So that's the first thing that we want to observe, and that we want to observe here. Another thing that we want to observe is, as I marked here, you can see that we are getting here, if I place my pencil here, you will see that there is a laser beam, there is a light ray here that's coming out of the right angle prism. The question is, what's happening here? What kind of light-related phenomenon can explain this behavior of light? So if we remove this right angle prism, you can see the footprint that I made. So there is something called total internal reflection that's taking place here. Total internal reflection is happening at certain conditions. The first condition that has to be fulfilled is the light has to be moving from the medium that has a higher index of refraction into the medium that has a lower index of refraction. In other words, the first medium has to be optically more dense than the second medium. The total internal reflection is taking place right here at this point. So at this point here, the light is passing through the glass that's optically more dense, and over on the other side, the second medium would be the air that's optically less dense. Now, at certain angles, you may establish the condition when all the light is actually going to be reflected off of this surface. In other words, it is not going to be passed into the air, and that's exactly what's that's happening here. So again, the light, here's our incident ray. It is not going to be bent because it's at incident angle equal to 0 degrees, and then it's going to enter here the glass, or the medium that this right angle prism is made out of, and then at this point here, at our point A, it's going to be totally internally reflected in this direction, and then it's going to hit the point B. At the point B, again, we have the light that's passing through the optically more dense medium, and it's trying to get out into the air, but due to the fact that all the conditions for the total internal reflections are being fulfilled, it's not going to be bent into the air, but it's going to be totally internally reflected here again in this direction, and then it's going to pass through into the air, and you're going to see it here as this beam. So what we're observing here is a specific phenomenon of total internal reflection that's taking place inside of this right angle prism. That's actually one of the reasons why we are seeing diamonds as a very sparkly, because the light that's entering the diamonds is being totally internally reflected, and it's giving this impression of a very sparkling and shiny object due to the total internal reflection that's taking place inside at internal surfaces of the diamond, similar to what we observed here with our right angle prism.